Hello. In this explainer, we're taking a close look at a professional assessment of the safety controls for emergency vehicles operating within a live aerodrome. We'll be examining just how effective these critical controls are in a high-stakes environment, and we'll focus especially on the gap between how work is designed to be done and how it's actually performed. We've structured this analysis into 5 key sections. We'll start by defining the task and its inherent risks, then we'll introduce the framework used for the assessment. After that, we'll explore that crucial difference between work as intended and work as done, diagnose some specific system weaknesses, and then we'll finish up with recommendations for strengthening these critical controls. So let's begin by setting the scene. Our focus is on the Airfield Fire Service, or AFS, and their vehicle movements. This is, by its very nature, a high-risk task. You have crews responding to emergencies, navigating active taxiways and runways, and they're often doing this under immense time pressure and sometimes in pretty challenging weather conditions. Now, the entire system of safety controls we're discussing is designed to prevent one specific outcome, what's called a materially unwanted event, or an MUE. This is defined as a catastrophic collision. The stakes are incredibly high, and really understanding this definition is central to evaluating how effective the controls in place truly are. From a technical standpoint, the primary hazardous energy that all these controls have to manage is kinetic energy. We're talking about the immense force generated by large, heavy vehicles in motion, the AFS, appliances, aircraft, and other ground vehicles all operating in a shared, complex space. So to evaluate these controls, the assessment uses a specific methodology. It's one that's designed to measure not just simple compliance, but true operational resilience. And here it is. This is the Resilience Control Score Framework. It's a tool that moves beyond a simple pass or fail metric by looking at controls from 4 distinct angles. This gives us a much more holistic understanding of their real-world effectiveness. Let's briefly walk through each of these quadrants. The first quadrant is robustness. You can think of this as the control's built-in strength. Is it a solid, engineered solution, like a physical barrier? Or is it what we'd call a soft control, like a procedure in a manual that relies completely on people doing the right thing every single time? Next up is human dependency. This quadrant looks at how much a control's success really hinges on perfect human performance. A control with high human dependency is just inherently more fragile, especially when people are under pressure. This third quadrant, alignment, is absolutely crucial. It asks a simple question from the user's perspective. Does this control actually make my job easier and safer? Or does it add complexity and get in the way of the work? A control that isn't well aligned is often the first one to be worked around. And finally, we have adaptability. This measures how well a control functions when conditions aren't perfect, during fog or at night. It also assesses how easily the system as a whole can recover if that control happens to fail. So using this framework allows us to really dig into the fundamental tension at the heart of this assessment, that gap between the official procedure and the on-the-ground reality. This slide illustrates those two perspectives really well. On one side, you have work as intended. That's the clean, linear process you'd find in a manual. It assumes perfect communication and that everyone follows the procedure to the letter. But on the other side, you have work as done, the complex, dynamic world where AFS crews have to constantly adapt. Safety in the current system isn't achieved by perfectly following a procedure. It's achieved through the expertise and the constant adjustments made by the people doing the work. And this is such an important point. The gap between intention and reality isn't a failure of the frontline workers. It's a property of the system itself. The system functions safely precisely because the crews have the ability to manage its complexities and bridge those gaps using their own expertise. With that context in place, we can now turn to the specific findings of the assessment. Let's have a look at how the critical controls performed when they were measured against this resilience framework. This overview gives us a high-level summary. Of the 7 controls assessed, 1 was rated as reliable, 5 were rated as somewhat reliable, and 1, which will be our primary focus, was identified as unreliable. That's the radio communication system. So now we're going to do a deep dive on this specific control, which received a score of just 2.3. With that score of 2.3, the radio communication system was clearly identified as the least reliable critical control. The core issues, as you can see summarized here, really stem from a weak robustness, meaning it lacks inherent engineering strength, and a very heavy reliance on human performance under pressure. Let's break down these vulnerabilities.
The assessment identified 4 key problem areas. First, success relies entirely on an operator hearing and correctly acting on verbal instructions. Second, drivers have to deal with significant audio clutter, trying to juggle communications from air traffic control, the Integrated Operations Center, and other agencies. Third, the radio layouts aren't standardized across the different vehicles, which undermines muscle memory in high-stress situations. And finally, some radios only become operational after the vehicle is started, causing critical delays.
This radar chart really visualizes the diagnosis. You can see the very low scores in robustness and alignment. This means the system doesn't have much engineered strength and it depends heavily on fallible human performance. And crucially, that low alignment score tells us that from the perspective of the frontline crew, the system actually makes their work harder and more stressful, forcing them to develop workarounds just to ensure safety. Understanding these weaknesses allows us to define a much clearer path forward. The goal isn't to demand better human performance, but to build a more resilient system that better supports the experts who are on the front line every day. The assessment concludes with 5 key recommendations. These are focused on reducing the cognitive load on drivers with technology like moving maps and accelerating engineered solutions that provide hard barriers, like runway stop bar alerts. It also recommends formalizing the collection of insights from the crews themselves and reviewing and simplifying communication protocols. But the last point really captures the strategic shift to prioritize robust engineered solutions over administrative ones that just place more burden on the operator. We'll leave you with this final thought. The findings here prompt a critical question for any leader or safety professional. How can we design systems that truly support and amplify human expertise, rather than systems that merely rely on that same expertise to compensate for their inherent flaws?